Welcome back, everybody, and I hope you had a great weekend. Unfortunately, the weather is what it is today. We can't do much with that. Hopefully, you will get a little bit more excited after the lectures today. Now, today, the topic is about logistic regression, which is our first encounter with classification problems. Now, till now, we have been basically looking at how we can fit a continuous function. Now, machine learning and making predictions and making fit to data is not only about fitting a continuous function. Actually, most of the applications deal with classification type of problems. And the most typical one is a case like true, false, yes, no, which you can easily encode in terms of 0 and 1s. So whether you are able to pay your credit card debt or not. So this is a famous data set, which is called the credit card data from, I think, from Taiwan. And in that case, you have something like 30,000 credit card holders. And the type of information, the features which you have, deal with the age, whether you occupied, education level, etc., etc. So there's something like 14, 15 features, which are then combined into a model in order to make a prediction whether this person is likely or not to pay the credit card debt. Another famous data set, which we have discussed many times, is a data set on cancer, on breast cancer, which is called the Wisconsin data set. And there you have something like 500 patients. And this is a data set which has been studied by many methods. And so you will encounter it again and again. And that data set has something like 30 features. And these features range from the thickness of the tumor, the color of the tumor, etc., etc. And these are classification problems in the sense that you want to use these features to say whether this is a benign or a malignant tumor. So typically, these type of problems are extremely important because when you run a scan of a tumor, you can have tons of images. And it would take an expert, which often is a pathologist, 1 or 2 days to go through the images. So if you can scan images by machine learning and then flag the cases which are dubious, then the expert, because a pathologist is often, and this is a worldwide problem, there are not enough pathologists. And this is the kind of expertise you gain through a whole life. So machine learning applied to this kind of medical images is a very popular application. And this would be a typical yes-no case or true-false, but you can have many more classes. So you can have, so when I say classes, these are the outputs. So you would have an output like 0, 1, true, false, or you can have handwritten numbers, which is another famous data set. And this is called the MNIST, after the American Institute of Standards, which has collected something like 60,000 handwritten numbers between 0 and 9. And then it's up to you to design an algorithm which recognizes these handwritten numbers as 0s, 1s, 2s, etc. In that case, you would have 10 classes. And how we actually set up a machine learning algorithm for dealing with that, this is what we will discuss now. Now, logistic regression is also an example which we will use as a stepping stone towards the next topic, which is neural networks and deep learning. And one of the reasons for that is that now we are not going to have analytical expressions for the unknown parameters beta. So we have to solve it numerically. And the standard way of doing that is by a famous algorithm after Newton. It's actually called Newton-Raphson because Raphson was Newton's assistant. So Newton got the credit, but Raphson did the work back in the 17th century. And this is one of the basic algorithms for finding optimal values. And that leads us to a topic which we will stay with for the rest of the semester. And that is gradient methods and gradient optimization. Because we are going to calculate the gradient of the cost function, or loss function. And that gradient is going to involve the second derivative, which we don't want to calculate. And this leads to different approximation strategies. And this is what we are going to encounter today, after we've gone through the mathematics of logistic regression. So logistic regression is one of the simplest classification algorithms you can think of. And it is actually linear for the model we make in the parameters, but it turns out into a non-linear model at the end when we take derivatives, which means that we have to solve the equations, the optimization problem, numerically. So in a certain sense, this is the encounter with real life in machine learning. So we leave the gentle analytical expressions from ridge and ordinary least squares to numerical solutions of the problem. If you look through the plans for this week, I have some suggested readings, and we are coming back to many of these texts. So don't be intimidated if I list too many pages, but these are pages which I will come back to. So in the textbook by Goodfellow et al., there is actually in chapter 4, and then later in chapter 8, there's a very nice discussion of the practicalities of gradient optimization. So we mentioned this in the beginning of the semester, that at the heart of all of machine learning, there is an optimization problem. And this is the one we are going to dive into now. So when we did linear regression, we got the feeling that everything is nice and sweet. We have nice analytical expressions, but now we have to leave that comfort zone and enter into the gradient methods. And this becomes very important for neural networks. So to be able to calculate derivatives of the parameters in an efficient way is extremely important. So this serves as a kind of overall motivation here. And then there are some videos which are more the kind of quick ones, which give you a quick overview of what we're going to meet. In the book of Rashka, in pages 53, 76, there's a more hands-on approach to logistic regression. And then in previous pages 37 and 52, they discuss gradient optimization. But we are going to look at these problems ourselves as well. And the plan for the lab sessions, as you probably have seen, so we are going to work on the bias variance trade-off, which you will need to implement in the project. And we are going to look at one method which is widely used for resampling of the data. And that's called this k-fold cross-validation. So we will dedicate some time in the beginning of the lab sessions, as usual, on that. And there's a recording from last week on the bias variance trade-off, which is a kind of important measure for when we overfit. Okay, and then obviously this is work on project 1. And I hope it's pretty okay what we are going to do now in this week. And everything you do now is something you will reuse in project 1. And also in project 2, etc., etc. So what is this logistic regression? So I'm going to jump into the whiteboard again. So let's slow down the pace a little bit and go into the whiteboard. And try to get a kind of feeling of what this method is about. So as I said, this is our first encounter with classification. And if you look into data sets, and this is a very important data set, which I recommend taking a look at. It's called Kaggle. You probably encountered this already. And there you will find tons of different data sets. Everything from classification of wines to analysis of football games and cancer data, etc., etc. Companies sometimes, they actually put a competition online on kaggle.com with their data. And sometimes there is even a prize if you come with the best possible optimization of the data which they have. And that prize can often be converted into some money, if sometimes. But take a look at that one, and that can serve also as inspiration for project number 3. So some of you may be a little bit at loss of what kind of data you want to analyze. And actually, many people have taken this course, they've actually looked into kaggle.com and they found data set they wanted to analyze. And some of the data sets have lots of scientific articles connected with them, which makes it easier when you're writing the project, because then you have data you can compare with and an analysis you can compare with. But let's take a look now at what we have done before. So in linear regression, the assumption we made about the data was that this y of I, which is given by a continuous function plus some normally distributed noise. So let me just remind you of things you've seen many times before now. So this f of x is assumed to be a continuous function. And in principle, if we don't put any constraints on what we have, then this x's could run from -infinity to +infinity, in principle. But normally what we have is a data set which is constrained by a specific domain. So what we have seen is typically that we have an x of A up to some x of B, and then we would have some y of A to some y of B. That is the typical situation which we encounter. But the function f of x is assumed to be continuous, and we assume that it exists. So what we did was simply to approximate this function with a given model where we have some feature matrix elements multiplied with the unknown parameter beta j plus some epsilon of I. And we label this one as a y of I tilde. So nothing new till now. And a typical parameter which we had, a set of parameters, if we took a first order polynomial, then we had a y of I, which we approximated with the intercept, plus some parameter beta 1, multiplied with x of I, plus this added noise epsilon of I. So this is the approximation which, one of the many approximations which we have studied. Okay? But now, we are going to look at a situation where this f of x of I is not given by a continuous function. So what about this y of I given by discrete values? So what we have then could be something like y of I, which only takes values between 0 and 1, where 1 could stand for true and 0 could stand for false. Or it could just be some output, which is in a table of some specific type of calculations where you only have a discrete output. So this could be if some of you is doing electronics, you may have encountered something which is called a NOT gate. So you send in bit 1 and you get out bit 0. You send in bit 0 and you get out bit 1. So the output of a NOT gate would just be zeros and ones. So it doesn't need to be a true-false case. Okay, this is a little bit different. So what we are assuming now is that we have discrete values. Now, suppose now that the data set looks like this. So we have some x's here, and we have 0 here, and we have some y's. And suppose now that we have some observations for x, for y. And then we have, so it takes only values between 0 and 1. So that means it's either 0 or 1. So we could have an observation here or here, like that. Now, in one of the examples last week, we had a function which was given by a cosine, and we did a polynomial fit when we studied the bias variance trade-off. And you saw that we could actually force the fit to go through all the points. But if we now stay with a straight line, suppose we go back to what we have here, and we want to use the straight line which we have here, and we want to fit this data set. There's nothing which hinders you doing that, okay? So I could now make a fit here with linear regression, since you got so excited about linear regression that you want to use it on everything you come across. This could now be a typical example of linear regression. So if you want to present this to your colleagues or friends, what would you say about this approach? It's not what you would present, right? I mean, you can always make a fit like this. And you see one of the drawbacks here is that your fit goes in principle from minus infinity to plus infinity. Whereas the data of y are constrained to 0 and 1. So the radical change we make now is to replace this function f of x with a probability. And that probability gives values between 0 and 1. And then we can say that when the probability is less than 0.5, we set the value of y to 0. So we can plug in a threshold function. So what you could do now is rather to fit another function, which could look like this, like that. And what you would do next is that you would say now that, okay, if my value is above a certain threshold, you output only 1. And if it's below a certain threshold, you output 0. And that's the basic entry point for logistic regression. So we are fitting something which we will treat like a probability distribution. So let me remind you quickly of probability distributions and how they are normally defined. So what we are going to do now is to replace, so we had y of I, which was given by f of x of I plus some epsilon of I. This is now going to be replaced by a y of I, which is given by p of x of I plus some epsilon of I. And that epsilon of I doesn't need to be normal distributed, because we are going to make a model for the probability. And when we have a model for the probability, that will dictate what epsilon will look like. Now, in our previous case, we assumed that epsilon was given by a normal distribution, and we said that f was a non-stochastic function. Now we replace this with a stochastic function. So some basic things about probabilities. What we have is when we integrate over a specific domain, is that d of x is normalized to 1. If you're dealing with a discrete probability distribution, then it's the sum over all the i's, elements of a specific set of events of x of I, and you want that one to be 1. The probabilities are normalized so that at the end, so if we now assume that x, let's just give an example here, that x is defined between 0 and 1, then one defines p of 1 to be equal to 1, and then p of x of I is smaller or equal to p of x of j when x of I is less or equal than x of j. So this is the kind of monotonous property of a probability distribution. You have other properties like the cumulative distribution, where you integrate up to a specific point, etc., etc. So these are some basic elements of probability of probabilities. One thing which is important when we choose a probability is that it can be normalized. So that means in principle that if the probability distribution is not normalized, then this 1 should be replaced by a number m, which is less than infinity. So that means that we can calculate an integral, okay? So let me just give you an example, a very simple example of a probability distribution, which is very much used in machine learning. And you will see why, I try to motivate why this is one of these popular examples. So let's just look at one case here. So we have example, and this is called the sigmoid function. I guess you've heard of that one, right? So that is the standard activation function in neural networks. And that probability distribution looks like a P. Now I'm just going to write X here. So this is given by some E of some parameter beta X, which I'm not specifying now, but later this is going to be the unknown parameters of the model. So this is a very typical function of beta of X. And when you integrate that from 0 to, let's say, infinity, so or up to a domain, so suppose now that X is element between 0 and A, so this is a domain where X is defined. And what you will find then is that when you integrate from 0 up to A of D of X, of E of X, times, and now I'm just putting beta equal to 1, just for simplicity. So 1 plus E of X, you will find that this has a finite value, which is given by ln of 1 plus E to the power of A. A as an exponent. Argument in the exponential function. So this is a finite function as long as A is finite here. And typically we would have domains where we have defined the X values in. Okay. So this is a typical example of a function which we could use as a probability distribution. Now we have only two cases. So we have the case with Y is equal to 1. And we could say now that the P of X for that specific case is equal to E of beta of X, of 1 plus E of beta of X. The other case, the other output is Y equal to 0. So since we only have two cases, then there are only two probabilities. Either Y is equal to 1 or Y is equal to 0. So that means that the probability in that case has to be 1 minus this P of X, which we defined here. And when I add these two, these sum up to 1. So this would simply be 1 divided by 1 plus E of beta of X. So that's pretty simple, right? So we are assuming that we want to use this for only two cases, Y equals 0 and Y equal 1. If you put Y equal minus 1 and plus 1, you just have to be a little bit careful with the scaling. But that doesn't lead to any bigger complications. Now, what does this mean graphically? What we are going to introduce now is a graphical representation of what is going on, okay? So we have a function, graphical representation, and this serves as a beginning step towards neural networks. So we would have a value, X of I, which we feed in to a function, which in this case is a probability distribution. So we are going to put in arrows, and we put in this function sigma, which now can depend on X and parameters beta, perhaps more parameters. And in our case, this is now given by this P of X of I, which I will also label as a P of I here. Then what we have is a threshold function. And this could be something like this, that if this function is smaller than a specific value, it doesn't need to look like that. It could look like this. So if it's smaller than a specific value, we just give the value 0. And if it's larger, we output 1. Okay? So this is typically a threshold operation. So you send in the input, and there is a function. This function sigma, which you have here, when we come to neural networks, so in the neural network language, this is often called an activation function. And this is very much inspired by neuroscience, where you have neurons. That's the reason why we call these neural networks. So you send in a signal, and then depending on the value of this function sigma, which depends on the input x, and also some parameters which you have, depending on the values which it outputs, then you decide whether this is 0 or 1. So that means that the neuron would fire a signal, or it will not fire a signal. So that's a very simplistic view of neurons in neuroscience. So much of the neural network machinery and the naming has been actually inspired by neuroscience. Now, in our case, you can think of these operations which we are doing now as you sending in some data, x, and this data x gets elaborated by some function, which you have decided to be your model. And then you have a threshold, which outputs a specific value. So that means that when you're done with this sends out your model y of I tilde. Okay? Now, this is a case where you just have one input, but we know that we have many inputs for one type of output. So let's now look at the general design matrix and how this graphical representation would look like if we think of the general design matrix we have been dealing with. So if we go back to the design matrix, if we now just set up the different columns and rows, so we have an x0, x01, up to x0, p minus 1. These are the features which we have. And as I said, in this credit card data, one column could be the age of the credit card holder. Another one could be the income of a credit card holder. Another one could be the level of occupation, unemployed, employed, student, not student, etc., etc. And then we have x2 of 0. And then in here, there is a column with xi, xi1, xi2, all the way up to x of I of p minus 1. And this continues all the way down to n minus 1 of 0. And then I have an x n minus 1 of p minus 1. So if we now look at one of these columns, no, one of these rows, sorry, and then we want to express this graphically, then I have to modify the graph which I made in the previous whiteboard here. So instead of one, I will have many more. So what you would have then would be an input which looks like as follows. So let me just bring this back again when everybody's been done with writing here. So this is the typical design matrix which we are setting up, and each column represents a given feature. So that means that the graphical representation now, we would have some xi0, we would have an xi1, and this goes all the way down to the amount of input data for that specific case. And these data feed in to this function sigma. In a simple way or a more complicated way. With a logistic regression, the function is not that difficult to see. And then I have my threshold function. And then I'm just marking the threshold with this symbol here. So that means that I'm going to extract a value either 0 and 1 or -1, +1, etc. And then I have my final output here of y of I tilde. And this is the quantity to be compared with the data, with the output which we want to train against with y of I. And this is where we are going to now have to define a cost function we can use for a discrete problem, a classification problem. So for the mean squared error, this is assumed to be a continuous function. And it fits very well the kind of linear regression cases we've been studying till now, where we fit a function. But let's now take a look at the classification problem. So I see that not everybody has drawn it. So you see the basic machinery here. And this is in the deep learning language or neural network language. This is called a simple perceptron model because you have just one type of neurons and we're not coupling many neurons together. So this function here, you can actually show that this function does well with linear fits. If you have nonlinear functions or more complicated function, it's going to fail. And there's an important theorem in deep learning, which is called the universal approximation theorem. So if we have more than just one layer, so what you would typically call this system here is just one layer, but then you can add layers, and these are typically called hidden layers, so which would be layers between your input and your output. And this universal approximation theorem says that you can approximate a continuous nonlinear function with at least one hidden layer. We are coming back to this. But the whole way of thinking, which I'm setting up there, this graphical way of drawing what we are doing, is something you will see now again and again and again when we start looking at neural networks in 2 weeks roughly from now. Okay, any questions so far? So does this kind of graphical concept or visualization, does it help? I think it's a useful way of thinking of what we are doing actually. So you feed in your data to some function, that function sends an output, and then we're going to compare that output with the data which we have. Now, before we move on now, what we need to say a little bit about is if we now assume that we use this function, so we have now defined a probability distribution, P of X. Now I'm going to be a little bit more explicit, and I'm going to make a simple model with unknown parameters. So I said that this beta, which we had here, we just left this beta undefined, okay? So we could now make a model for that. And we could simply say that we have an E of beta 0. So this is a probability for y equal to 1. For y equal to 0, it's 1 minus this expression, okay? So we could think of this as being a model where we have an x of I and 1 plus E of beta 0 plus beta 1 of x of I. Now, this sigmoid function behaves like a probability. And when you plot it, it's going to look like, so if you make a plot of this function, it's going to have this S shape. So it means that if you plot it between 0 and 1, so we have some x values here, and pay attention that the x's can also be negative. So this would typically continue, but if we now assume that the x's are positive only, it would have a shape between 0 and 1 here for, so this is y, oh, this is actually the probability, P of X of I. It would have a shape like this. So this is normally called an S shape. And we will put in a threshold here that if this function is below a certain value, we output 0. So the function itself is a continuous function between 0 and 1, but we are choosing to put in this threshold, saying that if it's less than 0.5, it just outputs 0. And if it's above, it outputs 1. So let's now simplify a little bit. So what we said is that we have for y of I equal to 1, then we have decided that this probability P of x of I is given by this function. Beta 0, beta 1, x of I. I mean, there's nothing which hinders you taking another function. You could just take a step function. The problem with the step function, as you will see, is that the derivative becomes problematic. So when you now are designing this type of functions, this P, what you often want to have is a function which has nice continuous derivatives. And you will see that when we are going to train a neural network, because then you have simple analytical functions which you can use together with one of the best algorithms ever, automatic differentiation, which then calculates derivatives to numerical precision using the chain rule and simple mathematical functions. So pay attention to this step, actually. So when you're designing this probability or this activation function, as we call them in neural networks, one of the things we want to have is a function which has nice analytical properties. Because when we train a neural network, you're going to call this function zillions of times, and you're going to calculate its derivatives again and again and again. So to have a model which is realistic, but also simple and gives nice analytical expressions is important. So simplicity is actually not that bad in most cases. But let's take a look at this, what we have now. So we have decided that P of I is now given. So if we now just simplify, I just call this P of I. So this is given by P of I plus epsilon of I, okay? The question now is, what probability does epsilon follow? So let's take a look at it. So what we decided is that when y of I is equal to 1, then it's equal to this P of I, which we defined, plus epsilon of I. Okay, so the probability is P of I. And P of I is given by this function here. And we have decided that when y of I is equal to 1, then this is the probability. When y of I is equal to 0, then this is simply 1 minus, actually it has a probability of 1 minus P of I. Sorry, no, it's P of I plus epsilon I. We are just setting up the probability here. And when we then look at what we have here, that means that this epsilon of I is equal to 1 minus P of I when y of I is equal to 1, and epsilon of I is equal to minus P of I when y of I is equal to 0. So this is just using the expressions, okay? Then what we want to do next is to calculate the expectation value of a given epsilon of I. So we have only two cases. So which means that we are going to have one probability, which is given by P of I. So the expectation value of a quantity like X is given by a sum over all the stochastic events which we have, multiplied with P of X of I. That is the formula for an expectation value of a variable x. So P of I is a probability which we have when y of I is equal to 1. And this is the value of epsilon. So this quantity here is epsilon of I. Then I have plus minus P of I multiplied with a probability, which in that case is something which we have defined for y of I equal to 0 to be 1 minus P of I. So that means that I have then to multiply this quantity with 1 minus P of I. And if I bring everything together, this is equal to 0. So it has a 0 mean value. Then I can calculate with this simple model the variance of epsilon of I. And the variance of epsilon I is the value squared. So the mean value is 0. So we would just be subtracting 0 when we look at the variance. So we would have this one multiplied with P of I. And then I'm going to have plus minus P of I squared, which is the value of epsilon I squared, multiplied with a probability, which is now P of I, 1 minus P of I. And if I add everything here, this is given by P of I, 1 minus P of I. Now, I know that roughly less than half of you have taken a course in statistics. So I don't expect that everybody will remember what kind of distribution has this variance. But there is a famous distribution. So we have some famous distribution like a Gaussian, normal distribution, Poisson distribution, Laplace, and so on. But if you've seen this expression before, is there anyone who remembers what kind of distribution has this as a variance? There is a famous distribution for two variables. The binomial. So what we would say then is that epsilon of I, in this case, follows a binomial distribution. Now, what we are going to do now is to make a model for the total probability. So how can we find these parameters, which you now look at these parameters beta? Is there a way we can find them? Well, we can find them in much the same way as we discussed the mathematical interpretation from statistics of ordinary least squares, ridge, and lasso regression. So the question now is, how do we find the parameters beta? So in our case, we had just two parameters, but there's nothing which hinders us of having many more parameters. So if I have many classes, I can make something which goes like beta 0 plus beta 1 times the first feature, beta 2 times the second feature, etc., etc. And it's pretty common to keep the argument to the exponential to be linear in beta. That's pretty common. You can make it more complicated if you want to. So what we are going to assume then is that we have a probability distribution. So our cost function is now going to be a function where we assume that the y of i's are independent and identically distributed. That's an important assumption. We define a domain of all the events, which now contains an x0, a y0, there's an x1, a y1, etc., all the way up to xn-1 or yn-1. And now we are defining a probability T of the whole domain with some given parameter beta. So given beta, we have a probability distribution. And again, we are going to set this up as the individual probabilities, But now we are going to introduce this binomial model. So we're going to make a model here. And that model is now going to be given as a product over all the possible outputs which we have. This P of I, which we have here, I'm just going to repeat it. So P of I is equal to the probability of beta 0, this simple model in terms of the betas of X of I, divided by 1 plus E of beta 0 plus beta 1 of X of I. It's going to be given by the power of Y of I. And remember now that Y of I can be either 0 or 1. So if it's 1, it's, as we said before, it's just P of I, okay? But then we have the other case which we have to take into account, because not all the Y's are 1s. So we need to multiply this with 1 minus P of I, and then we have I minus Y of I. Because we don't have 1s only. So we have the data which we have, the outputs, is normally a mix of 0s and 1s. So we have to take into account the different probabilities. And we assume that these P of I's refer now to independent and identical redistributed events. But we have to take into account the fact that we have a binary model, okay? So this is the function which we are going to use. And then what we are going to do now is to find the optimal beta so we can maximize the probability. And this is where we stop now before we take a break. So we have P of these terms of a P of D of beta. This is going to define our cost function. Or we can find beta as argmin, and this is the equivalent problem of minus log of the cost function beta for all the parameters beta. So we have made a model for this probability where we threshold the output. If it's above 0.5, we send out 1. If it's below, we send out 0. And there are only 2 possible events. So this is a model which we are cooking up. It doesn't need to reflect reality, but it's a good approximation. And it works pretty well in many, many applications. Does that sound reasonable? So this is just the mathematics of the model which we now want to optimize. And as you can see from the mathematical form, which you have here, with the parameter beta not being set up in a linear way in front of the design matrix, this is normally going to lead to expressions which don't have a nice analytical solution, like we had for standard linear regression. And we will have to solve the equations for beta numerically. Okay? So after the break, we are going to set up the equations we end up having to solve. Okay, I went a little bit over time here, but I just wanted to set up these equations. Let me pause. So before the break, we made a model for the probability. And this is inspired by kind of knowledge which we have about this kind of probabilities. And we are dealing with a binary model only. When we have more classes, we will need to modify this function here. And we're coming back to a little bit later to that in connection with neural networks. But now we're going to stay with this simplified binary case. So we have only 2 outputs, true, false, 0, 1, etc. And the model which we made is now based on us replacing a continuous function with a probability distribution. And this probability distribution takes a simple form with only 2 unknown parameters beta. So we can, if we have more features, for instance. So this xi could be the first feature. It could be, if you're looking at cancer data, it could be the thickness of the tumor. Then we could obviously add a beta 2 times some new variable, etc., here. But now we just stay with this very simple model, okay? So this means that what we want to do now is to optimize the log of that product of probabilities. Because to optimize the product itself of these probabilities becomes a little bit more cumbersome. And it can also lead to sometimes to numerical problems like loss of numerical precision. But let's take a look at the mathematics which we are going to end up with now. So if I take this expression here and we go back to what we have plugged in, which is this expression. So we are taking the log here, so that gives us a sum. So the first term is just going to have a y of I times p of I multiplied with the log of this quantity. So the first term is going to give us, so we are going now to calculate the cost function as a log, which is minus, so I actually was a little bit too fast here. So the cost function is now going to be this probability. So this is our cost function, C of beta. So when we do that, we get now a sum over all the data points which we have. And the first term gives us a y of I, and then I have a log of p of I. So remember now, if you go back to what we had before the break, let me just remind you of that. P of I is given by this term here. And we get an additional term, which is plus. And then I have 1 minus y of I. And then I have log of 1 minus p of I. Let's put parentheses here. And now I'm going to put in the explicit model for p of I. So the expression now is pretty generic. We have to specify the p of I we are going to plug in. So when I do that, you know that if I take the ln, let's just do this into log of this e of beta plus beta 1. Let me just do this intermediate step here. So we have everybody with us. And we know that this one, the first term, is just beta 0 plus beta 1 of xi. And then I get a minus, and then I have L log of 1 plus E of beta 0 plus beta 1 of x of I. So that's just an intermediate calculation. And with that one, we can go back to the equation which we have. And what we are going to get then, so this means that this cost function, when we plug in this specific expression for the probability, we have a sum of I equals 0 of n minus 1. And then we are going to have a y of I. And then I have just multiplied with beta 0 plus beta 1 of x of I. And then I get minus. And then I'm going to get a log of 1 plus E of beta 0 plus beta 1 of x of I. And that's the final expression. So this is much simpler than just a product of all these probabilities. And this is something which we can calculate the derivatives of. So we have only two parameters now. And the thing which I want now is a dc of d beta 0. We want that one to be 0. And the same with beta 1. So this is our optimization problem. So if I take the derivatives, the first term is pretty easy. So when I calculate the derivatives now, we are going to get two simple expressions. And if we add more parameters, betas, it's not so difficult to see that we are going to get something which we can rewrite in terms of a null matrix, which is our feature matrix. But then we have to be a little bit careful now because we have a probability here, which we need to pay attention to, because the probability has the parameter beta, the unknown parameters, as an argument to an exponential. And this is one of the reasons why we will not get a nice analytical expression for the unknown parameters beta. So when I take the derivatives now, the first derivative, if I take dc of d beta 0, and I want that to be 0, that's going to be given by minus I equals 0, n minus 1. And this is y of I minus p of I. And remember now that p of I is this probability which we have. So let me just quickly remind you of that. Then I can take the derivative of the next quantity, which is dc of d beta 1. And we also want to drive that one to 0. And that's going to be given by a sum of I equals 0 to n minus 1. And then I'm going to get an x of I, and then y of I minus p of I. So I can now, if I have more parameters, or I can actually set this up in terms of a matrix vector formulation, and it's actually not that difficult to see. So in general, for the gradient G, and now this is a vector, so I'm putting it up as a bold-faced quantity of dc d beta. This is something which is going to take the following form. So we want this one to be 0, but it has an analytical form. So let me just set up the form which follows from what you see here for beta 0 and also for beta 1. So what we are going to get then is a quantity dc of d beta, which is going to be given by minus x transposed times y minus p. So y and p are two vectors, and they have a length of n. And if we go back to the design matrix, we know that this quantity has dimensionality n times p. And if we take the transpose, it's p times n. That means that this gradient, which is now given by dc of d beta, is actually a vector of length p, as it should be, as we had in linear regression. But the problem now, as you can see, is that we don't have a nice expression for the beta. So beta hat is included in P. When we did linear regression, we actually had only a linear dependence on beta. And that means that we could actually separate easily beta and get a nice analytical expression. Now, this expression here is something we have to solve numerically. I also wanted to add a new quantity here. So we can, in linear regression, there we found that the second derivative of the cost function, and this is a matrix, which we call the Hessian matrix, is given by 2 divided by n depending on how we define the mean square error. So this was called the Hessian matrix, the second derivative. And pay attention to one thing now. And this is what complicates life when we are going to look at the algorithm for solving the equations for optimal beta. So if you look at what we have here, this one is independent of beta. It contains only the data which we plug in. But now I'm going to give you the equation. And if you want to, you can take that as an exercise. It's always irritating when people say, you can easily show this. But it requires some efforts, as you saw in one of the exercises, the weekly exercises. But you can show that this one is now given for logistic regression, log reg, times x, where this wi, the diagonal matrix elements, are given by p of I, or 1 minus p of I, and the non-diagonal elements, when I is different from 0, is equal to 0. So this is a matrix which has only diagonal elements, but you see now that the second derivative depends on the parameter beta, the unknown parameter beta. And this is what is going to lead to problems to us when we now introduce Newton's method. So have you all met Newton's method or Newton-Raphson's method? Let me remind you of that. The derivation of Newton's method is extremely simple. It's a Taylor expansion around the point, and you stop at the second derivative. That's the method. So let's look at how we can find these parameters beta. So pay attention now, because when we do logistic regression here, then the second derivative depends on beta. So now depends on beta. Okay. So how do we solve these equations for beta? So how do we solve the equation for beta? The equations for beta optimal. So the method of choice is Newton's method. And let's just remind ourselves about Newton's method. And now I'm going to simplify life a little bit by simply assuming that we have only one variable beta, okay? So there is no gradient. There's actually only the first derivative and the second derivative. So let's remind ourselves about Newton's method, or Newton-Raphson's method. Newton-Raphson. You'll be surprised, or perhaps even disappointed, to hear that this is the basic entry point for most of the machine learning optimization. Okay? So let's now assume that beta is single valued. So beta is a scalar. So beta, in this simple example, is a scalar. So that means that the cost function dc of d beta goes simply over to dc of the one specific value beta. So we don't need to take into account the partial derivative. We have only one value of beta, okay? So that is the gradient we defined previously. And what we are going to do now is to make a Taylor expansion. Around the optimal value. So I'm going to make an expansion around beta, and I'm going to label the value before or the value around the optimal one for beta of n. Now, this n is something which I later will define as an iteration, because you solve this method iteratively. Okay, so that means that when I do that, I'm going to get a cost function, C of beta, and this is just a plain Taylor expansion. I'm going to make I have a constant term, which just depends on the term beta of n. And then I have now the first term, which is obviously the derivative. So I'm going to call this as a derivative, which depends on beta of n. So this is now just d of c of d beta, calculated at beta equal to beta of n. And obviously then I have to multiply this one with the optimal value minus the difference. So minus the previous value, like that, okay? And then I have a second order term and higher order terms. So let me just put a parenthesis around this one. And then I have plus. And when I take the second derivative, what I'm going to get now is the, obviously we get a second derivative, so we have a half. And the second derivative is just given by this quantity we call the Hessian, but now it depends only on one value of beta. So this is now the second derivative of d beta, and calculated at beta equal to beta of n. And then it has a beta optimal minus a beta of n. And now this is squared. And then we have higher order terms. It's just a Taylor expansion, right? Does everybody recognize that as a Taylor expansion? Okay. So what I do next, I just introduce a new variable, just compactify the equations minus this beta of n, just to make life a little bit simpler. So what I have then is an expression. If I put everything together, let me see what people have written it down. Okay, can I switch page? Is that okay with everybody? So what I get then, when I now just introduce this parameter b, I have the expansion, I have a constant term. So this is something which we know. So this b beta of n is known. And then I get the first derivative, which I call for a g. So I have this g, and this is evaluated now at this beta of n. And I'm going to make this a little bit more compact. So this is a g evaluated at beta of n. And this is multiplied with the parameter b, plus 1/2 times b squared. And then I have this second derivative, which I now just label as h of n. And this is h as a parameter of beta of n. And now I approximate to second order only. So I leave out all the higher order terms. And then I take the derivative. So now I require dc of db equal to 0. I take the derivative of that quantity, so I get a g of n plus, and then I have an h of n times b, and I want that one to be 0. So that means that b, which is equal to beta minus beta of n, is equal to this minus, and then I have of n inverse multiplied with g of n. And now I'm going to assume that I solve this iteratively. So I start with a guess of beta 0. And then that means that my beta optimal is now simply going to be replaced by iteration n plus 1. Okay? And if I do that, I reorder. So I find that beta of n plus 1 is actually beta of n minus, and then I have this quantity n here, inverse, multiply with g of n, and this n takes values from 0, 1, and up. So we would start with a guess, beta 0. And then we continue till the difference between beta of n plus 1 minus beta of n is smaller than a number we have fixed. So we would start with a guess. And you will see that these methods, which we will discuss in more detail next week, with examples, numerical codes, etc., are very sensitive to the initial value. And they're also very sensitive to the derivatives. So we start with a guess. So the guess is very important, beta 0. And 2, we iterate over n till this difference between beta of n plus 1 minus beta of n is smaller or equal to a number epsilon, which can be something like 10 to the minus 8, etc., just as an example, till this test is satisfied. Now, one thing which you guys probably noticed in project 1 is that when you run lasso regression, sometimes you get a message that it hasn't converged. So how many of you have gotten that message when you run scikit-learn? Yeah, I can see that. So this is actually the convergence test of Newton's method. So what you have here, this equation here, is nothing but Newton's method. And this is the basic method which we typically implement in machine learning optimizations. Now, the problem which we face is actually that this H is a matrix. So if you have 1,000 parameters, it's a 1,000 by 1,000 matrix. And you don't want to invert that matrix because you have to calculate the second derivatives of the parameters. And also the gradient itself, as you will see, is complicated enough. So when it comes to real life implementations, so I did a derivation just for a scalar, but in general, the general case, so in general, H is a matrix, H of beta of n is a matrix. G of beta of n is a vector. So G is something which we decided has a dimensionality given, or length given by P, the number of features. And H is a matrix of dimensionality P times P. This means that beta, which has length P, gives us a recipe n plus 1, which is equal to beta of n here, minus, and then I have to invert a matrix of beta of n, multiplied with a vector given by beta of n here. Sorry, that was a little bit messy here. So let me try to write it in a cleaner way. So now we have to perform a matrix multiplication. So think of you having 100 parameters. That means the following. It means that you will have 100 such equations. And suppose now that you just run this with 1,000 iterations. Suppose little n here is equal to 1,000. So that means that you do these operations here 100 times 1,000 times. And since the matrix H depends on beta, you have to calculate it every time. And the matrix is now a matrix, since we have 100 features, it's a 100 by 100 matrix. And you see that this becomes unwieldy. When we come to neural networks, you're going to have tons of parameters. And the parameters can be in the order of millions. If you look at large language models, you have trillions of parameters. Trillions. So even for the cases you're going to look at with thousands to 1,000,000 parameters, this is going to be a heavy computational exercise. And this is where the bottleneck in all of machine learning lies. So I can tell you that if you can cook up a smart algorithm for evaluating these equations, you will get many more friends. And I'm not inferring that you don't have friends, because these will be friends who will cite you. So one of the methods which we will encounter next week is called ADAM. It's an adaptive method. And that was introduced in 2014, and it has 200,000 citations. A good scientific article, a good one, a decent one, has between 100 and 1,000. So this has 200,000 citations as of now. So that says everything. So how do we deal with these methods? Because you see now quickly, you don't want to calculate the second derivative of the cost function. You don't want to invert this matrix. So the standard approach, which you will deal with, is actually to replace the inverse of the matrix with a parameter. Which I will just call gamma of n. So that means that we get a recipe where we have beta of n plus 1 is given by beta of n minus this parameter gamma of n multiplied with the gradient. Even the gradient can be problematic to evaluate because we have to update it every time we perform an iteration here. So this parameter which you see here is called the learning rate. So you learn how the gradient moves on. And often what you would do is to either you can keep it fixed, and in many cases it's cheaper to run a neural network calculation with many parameters gamma and simply pick the one which gives you the best result. Because it's cheaper to rerun the network instead of calculating the derivatives. So what often people do is to set this gamma with a grid of values. So it could be something like 10 to the minus 5, 10 to the minus 4, up to, let's say, 10 to the minus 1. And this is going to mimic your second derivative matrix, which you have to invert. Okay? So many people get disappointed when they see this because at the end, we're just tuning parameters. But the problem is that the computational complexity becomes very large when you have millions and millions of parameters. And then simply to evaluate this matrix, which you have to invert as well, becomes extremely time consuming. So anything which can improve this machinery and evaluate this parameter gamma in a more reliable way than those which we are going to present in the next weeks is something which can make you famous. Because if you think of these huge machine learning models, like the big language models. You're simply implementing these gradient descent methods to find the optimal parameters. And the electricity bill is enormous. So even from an electricity bill point of view, to finding smarter algorithms is something which will actually save a lot of electricity. That's something which we often tend to forget, that in the training of these models, we're actually using high performance computing facilities, which whose electricity bill is not negligible. Okay, any questions so far? I hope you see the basic. I want to give you the basic overview and the important entry point, which we're going to spend quite some time on in the weeks which are coming. Yeah. I replace the inverse of the matrix. So this is just a constant you will plug in front of the gradient. And the gradient itself is also something which we are going to simplify the calculations of by using something which is called stochastic gradient descent. So this is something we will discuss in more detail in the next coming weeks. But now we're going to stay with this a little bit simpler analysis. And one of the things we can do now is actually to look at some simplifications. So we are going to perform the expansion around the expression here. So the question is, can we find an optimal beta? No, sorry, not an optimal beta, but an optimal gamma. So there is a simple way of getting some kind of feeling for what is the optimal gamma value. So we go back now to the Taylor expansion. So Taylor expansions are extremely useful tools. So we expand now the cost function, this C of beta, around this beta of n minus gamma, and now just write G of n here. So G depends on beta of n. So I do a new Taylor expansion. And what I get then is a Taylor expansion of the following type. So I get a beta of n minus a gamma of G of n. And this is obviously given by a constant first, beta of n. And there now I have the parameter gamma, and G is a gradient. So I have to be careful now because this is a vector, so I have to take the inner product. So it's not a scalar anymore. If you replace it with a scalar, it's much simpler, then it's just G squared. And then I have the next term, which goes like 1/2 of gamma squared. And then I have my G of n, and this is transposed. And now it's multiplied with this matrix, the Hessian matrix of n. And this is multiplied with G of n. And then I have higher order terms. And again, I just leave out the higher order terms in gamma. And I'm going to simplify notation here. So I say that G of n is now replaced by G, and H of n is now replaced by H. And then I take the derivative with respect to gamma. So derivative with respect to this gamma. So I take this d of c with d gamma, now gamma. And I want that to be 0. And if I do that derivative, what I get then is that gamma is equal to g of t times g divided by g of t times h times g. So that's the optimal for every value of n. So keep in mind now that I suppressed the n dependence. So this is actually something I could calculate at every iteration. This actually has a name in the literature. So for those of you who have studied optimization theory, this is a method called steepest descent. Any one of you have heard of that? So if you go into textbooks on optimization theory, you will encounter tons of ways of actually solving this type of problems. Now, this one is still a nasty problem because I have to evaluate the gradient and I have to evaluate the second derivative, right? So it's not something you would do in your actual implementation because you still have to, if this is a matrix of dimension 1,000 times 1,000, or even 1,000,000 times 1,000,000, you don't want to do this. In a neural network, you have millions of parameters. But now we can make a simple assumption. So this is just an assumption. So we could assume that this h times g is given by an eigenvalue. So this g is an eigenvectors of h. This is normally not the case, right? But let's assume that. So if you do that, then you will get a simpler answer, because then you're going to get that gamma is equal to g of transpose times g. And then I have g times the eigenvalue times g. And that is simply 1 divided by the eigenvalue. So that gives you a kind of minimum and maximum value if this matrix H with these eigenvectors has a minimum eigenvalue and maximum eigenvalue. So this gives you a gamma min, which you can set up in your iterative solver, which is given by the maximum value, and then a max, which is given by the minimum value. Now, if we can diagonalize the Hessian matrix, you can actually show. So I'm just stating a result from linear algebra and from this type of convergence problems. There is actually a precise mathematical statement you can make. So if you can diagonalize H, and now keep in mind that this is something which changes for every iteration. If you're doing linear regression, it does not. Then it's fixed, because then in linear regression, the second derivative is the design matrix transposed times the design matrix. And there is no dependence on the unknown parameters. But any other method will have a dependence on the unknown parameters. But if you can diagonalize it, then you can show that this gamma has to be smaller than 2 divided by lambda max. So this is a result from linear algebra, which we are not going to prove, but I'm simply stating it. And if you can do that, if the problem is not that big, yes? Yeah, if you can diagonalize it. But keep in mind now that this matrix depends on the second derivatives with respect to the parameters. So you have to calculate the second derivatives as well. And that has to be done numerically. So even for 100 by 100 matrix, and you would have to do this at every iteration. So if you do it 1,000 times for every parameter, you would have to diagonalize this matrix 1,000 times, and this matrix is 100 by 100. And every time, since the parameter beta change, you have to update the derivatives. Because the elements of that matrix are given by the second derivatives of the cost function. So you see now why in machine learning, unless you can actually find these eigenvalues, you simply start with a guess for the parameters, And then you just rerun the calculations and you tune these parameters so that your error functions, like the mean squared error, or in classification problems, it's something called the accuracy, which we will define next week. If they get as close as possible to the ideal value, then you choose that parameter which does the best job. Say again? No, you would not do it. But there are methods which allow you to precondition. They're called preconditioners. So you would use something like a quasi-Newton method. But essentially, everything we are going to encounter next week and the week thereafter is us finding ways of updating this parameter gamma with some information about the gradients. The simplest brute force way is just to run the calculation with constant values and then pick the one which gives the best fit. Simply because that's cheaper computationally. So I hope you don't get disappointed. There are many people who get disappointed when they hear this. But you see quickly that when you have parameters with millions and millions to deal with, then we have to find ways to make life simpler. Okay? So at the lab, we are going to discuss cross-validation and also obviously work on a project. And next week, we are going to look at many of these methods. And if you can find some smarter ways of doing that, then fame is guaranteed. Okay, guys. Have fun, eh? Good to see you again.